Hey, what's up everyone? Welcome to Electrochemistry Part 2. Today we're going to be looking at how to balance a redox reaction. And to understand why we need to learn to balance redox reactions, I'm going to show you a certain redox reaction. In this case, you have C3H7OH, which is isopropyl alcohol, reacting with Cr2O7 which is dichromate, to produce a chromium ion, and C3H6O, which is acetone. Now, if you notice, this whole thing is not balanced. Elements aren't balanced, charges aren't balanced, nothing's balanced. And the reason why it's not balanced is because redox reactions usually happen in some sort of solvent. And when redox reactions happen in that solvent, those solvent molecules are involved in the reaction. And so this reaction here, or this chemical formula here, kind of only shows the major species that's being reduced and oxidized. It doesn't really talk about all the other elements that are going into making this reaction happen. So depending on what solution this redox reaction is occurring, you're gonna have different processes for how to balance them. The first one we're gonna look at is if this redox reaction happened in an acidic solution. So the first step is to split the skeletal equations into two half equations, or two half reactions. And so which ones are we dealing with? We're going to be, this one is going to be paired up with this one, and that one is going to be paired with that one. So what we're really looking at is the carbons are staying the same, or so C3H7OH is going into C3H6O. And then we have Cr2O7 to Cr3+. And obviously some of these are the ones being oxidized and reduced. And so that's why we want to split them up into half reactions. That's the first step. The second step is to balance all the elements except for hydrogen and oxygen. So if you look at the first half reaction here, the carbon here is the only element except for hydrogen and oxygen. And there's 3 carbons on the left, 3 carbons on the right. So this is good as is. If you look at this one though, the chromium, there's 2 chromiums on the left-hand side, but only 1 on the right-hand side. So let's add a coefficient of 2, and that's the second step complete. It's to balance all the elements except for hydrogen and oxygen. The next step is to balance oxygen using waters. So if you look at the first half reaction here, you realize that there's 1 oxygen on the left, 1 oxygen on the right. Both the reactants and the products have 1 oxygen, so we don't really need to balance anything. But on the second reaction here, you have 7 oxygens on the reactant side, but none on the product side. So let's add 7 waters to balance out all the oxygens. But of course, whenever you add those hydrogens, you create an imbalance of, whenever you add those waters, you create an imbalance of hydrogen atoms. So how do you balance the hydrogen atoms? You balance hydrogen using H+ ions. And so let's do it for both of these. In the first step, in the first half reaction, you have 8 hydrogen atoms. That's 7 plus 1. But on the product side, you only have 6. So let's add 2 H+ ions. And then on the bottom, you have no hydrogens on the left, but 14 hydrogens on the right. So let's add 14 hydrogens on the left. And the reason you're allowed to use H+ ions is because, remember, this is happening in an acidic solution. So in an acidic solutions, you have a lot of H+ ions that are freely available to react. That's the whole definition of acidity, or one of the definitions of an acidic solution is that it can liberate H+ ions in solution. So in an acidic solution, you have an excess of H+ ions that are available to react to make redox reactions happen. Alright, so that was step 4, to balance hydrogens using H+ ions. So far we've balanced the elements, we've balanced the oxygen, we've balanced the hydrogen. That's it for the elements, but what else do we have to balance? We have to balance charge. So we have to balance charges using electrons. This is where the whole redox reaction comes in from. Remember, a redox reaction involves an electron transfer. So you have to have electrons in order for this to be a redox reaction. So on the left-hand side of the first reaction, you have a charge of 0. On the right-hand side, you have a charge of 2+. So let's add 2 electrons on this side. And then on the bottom here, you have a charge of -2 plus 14. That's a charge of 12, positive 12. And on the right hand side, you have 2 of these chromium 3 plus, so that's a charge of +6. So in order to balance these out, let's add 6 electrons here, so that the charges on both sides are both 6 plus. So that's how you balance the charges. And now I guess the final steps would be to make all this come together. Add these all up into one final equation. But before we can do that, we need to get an equal number of electrons on both half reactions. Remember, in our final redox reaction, we're not allowed to have electrons. So let's make sure both of our half reactions have the same number of electrons before we add them up. So the bottom one has 6 electrons, the top one has 2. So if we multiply the top reaction by 3, that should get us 6 electrons, and we can keep the second one the same. So let me write this down. We have 3C3H7OH, 3 isopropyl alcohol going into or reacting to produce 3C3H6O, which is acetone, and then we have 6H plus and 6 electrons. That's the first reaction, and of course the second reaction stays the same because we already have 6 electrons. So we have Cr2O7 2- dichromate with 14H plus and 6 electrons to form 2 chromium ions and 7 waters. If you notice, on one of the equations, the first one, there's electrons on the right hand side, on the product side. This means that this half reaction is actually the oxidation half reaction. In the oxidation half reactions, remember, your electrons are produced. Your species gets oxidized to form electrons. And so the bottom one takes those electrons in and it reduces the chromium here. So this is the reduction half reaction. That's the oxidation, that's the reduction. Oxidation produces electrons, reduction uses those electrons up. Alright, so now we're ready for the actual final step, which is to add both half reactions. And so let's do that. Let me get a different color. Let's get purple. Alright, so we have this. The electrons, of course, cancel out, but what else cancels out? We have 6 H pluses here, but we have 14 here, so we can just get rid of that and be left with 8 H plus, and that seems to be everything that we can cancel. So let's write out the final reaction. So 3 C3H7OH plus Cr2O7 2- plus 8 H plus produces 3 C3H6O plus 2 Cr3 plus and 7 H2O. Almost ran out of space. But yeah, this is it. As you can see, the redox reactions tend to be a little complicated and a little involved, but the first equation that we had, if you go back, this one on the top, this one's usually just there for, I guess, your own viewing. It makes it really easy to see which one's being oxidized, which one's being reduced. But if you want to know how the redox reaction is actually occurring, you have to write out this entire balanced redox reaction. But of course, all of this was under acidic solution. So if I give you another redox reaction, in this case you have the chromium ion reacting with manganese oxide to produce the manganese ion and chromate. Let's try doing this in a basic solution. In a basic solution, you're not going to have access to those H plus ions that we had in acidic solutions. So we're going to have to come up with a different way to balance your hydrogen atoms. But of course, let's get to that. The first couple of steps for balancing in a basic solution are very similar to an acidic solution. The first one is to, of course, split the skeletal equation into 2 half reactions. This is the skeletal equation, by the way. That's what it's referred to. So let's split it into 2 half reactions. Let's keep the chromiums together. So chromium 3 plus to chromate. And then we have the manganese oxide producing manganese ion. And so those are your 2 half reactions. Your second step is, of course, to balance the elements except for hydrogen and oxygen. But luckily for you, the chromiums here are balanced, the manganese here are balanced, so we don't have to do anything. 3, balance oxygen using hydrogen. So let's see, in the first half reaction you have 4 oxygens on the right hand side but none on the left, so let's add 4 waters. We add 4 waters to balance out the oxygens. And then on the bottom one you have 2 oxygens on the left but none on the right, so let's add 2 waters. And that's your oxygen balanced. But of course, this is the step we've been worrying about. How do you balance the hydrogens? You don't have access to your H plus ions like you did before, so how are you going to do it? Alright, so you balance hydrogen by adding water to the side needing hydrogen and then adding OH minus to the other side. So how does this work? Alright, let's do it. On the first one, you have 8 hydrogens on the left-hand side and none on the right-hand side. So on the right-hand side, let's add 8 waters. You've added 8 waters to the right-hand side, and the same amount of waters that you add, you need to add the same amount of hydroxide ions to the other side. So essentially what you're doing is that whenever you add a water on one side and an OH on the other side, you're effectively just adding a hydrogen atom to one side. So what we're effectively doing is adding 8 hydrogen atoms on the right-hand side without using any H+. Because remember, in a basic solution, we don't have access to H+. What we have access to is water and hydroxide ions. And so you can use both the water and the hydroxide ions. If you notice, the only difference, the difference between the elements in water versus hydroxide is just a hydrogen atom. So you can balance the hydrogens by adding waters and hydroxides. Notice that even though we need 8 hydrogens on the right-hand side, we add 8 waters, which add 16 hydrogens, because we end up taking 8 hydrogens away by adding the 8 hydroxide on the reactant side. So that's how you balance hydrogen in a basic solution. Let's do it again for the second half reaction. On the left-hand side, you have no hydrogens. On the right-hand side, you have 4 hydrogens. So let's add 4 waters on the side needing hydrogen, and then on the other side, let's add a hydroxide. So what this effectively does is that it adds 4 hydrogen atoms to the reactant side. That's all that it's effectively doing. And so whenever you're balancing in basic solution, there tends to be like one more step, which is kind of a house cleaning step, which is to cancel like species on opposite sides of the arrow. So if you notice, you have hydrogen or you have waters on the reactant side and the product side, so we can kind of get rid of that. There's 4 waters on the reactant side but 8 on the product side, so this is the same as 4 waters on the product side. So let's write that. We have our chromium ion with 8 hydroxides producing our chromate ion, and then 4 waters. And let's do the same for the second half reaction. You have 4 waters on the left and 2 on the right, so we can just have 2 on the left. So you have manganese oxide with 2 waters producing your manganese ion and then 4 hydroxides. And those are your like species canceled. And what we've effectively done is we've balanced all the elements. That's only half of the story. We need to balance the charges too. So 6 is to balance charges using electrons. If you notice, for the first half reaction, you have a charge of -5 on the reactant side, 3 from the chromium, and then -8 from the hydroxide. And on the right hand side, you have a charge of 2-, so -2. So in order to balance the charge, let's add 3 electrons to this side. And then for our second half reaction, you have a charge of 0 on the left hand side and a charge of -2 on the right hand side. Because of that, manganese is 2+, and then you have 4 hydroxides, which are each -1. So 2 minus 4 is -2. And so in order to balance these out, let's add 2 electrons to the left-hand side. And again, the same thing that we noticed with acidic solution happened to basic solution. In one of these reactions, you are producing electrons. So this is the oxidation half reaction. And then in the bottom one, you are using up electrons. So this is the reduction half reaction. One is the oxidation, one is the reduction. It'll always be like that. All right, now that we've balanced the elements and the charges, we need to find a way to bring these all together. And in order to bring this all together, you need to have the same number of electrons on both half equations. So how would we do that? Let me get a different color. There's 3 electrons on the first, 2 electrons on the bottom. So if we get 6 electrons on both, we can cancel them all out. We can get 6 electrons on the first one by multiplying everything by 2. So you have 2 chromium ions and 16 hydroxide ions to produce 2 chromate ions, 2 minus, and then 8 water, and then 6 electrons. And then for our second half reaction, you can multiply this by 3. Remember, we're trying to get 6 electrons, so we have to multiply by 3 to get 6 electrons. That's 3 manganese oxide and 6 water and 6 electrons. That's producing 3 manganese ions and 12 hydroxide. And now we have to add these all up. We have the same number of electrons, so they'll cancel out at the end. And all we have to do is add them up. So the electrons cancel out. What else cancels out? We have 2 hydroxides on the right-hand side, but 16 on the left-hand side here. So we can just have 4 hydroxides on the left-hand side. You have 6 waters on the left-hand side, but 8 on the right. So we're just left with 2 waters, and everything else looks good. So let's write this all up. Oh my god, this is going to be long. 2Cr3 plus 3MnO2 plus 4 hydroxide, 2 chromate ions, 3 manganese ions, and then 2 waters. And that's your balanced redox reaction in a basic solution. So remember, in acidic, the only difference between acidic and basic is how you balance those hydrogens. You balance hydrogens in an acidic solution by adding H+, and in a basic solution, you balance out the hydrogens using H2O and hydroxide on separate sides of the equation. So that's the only difference between acidic and basic solutions, and you get your final redox reaction, which helps explain everything, the elements, the charges, how everything works. And that's about it. So you learn how to balance redox reactions in acidic and basic solutions. I hope this is helpful. I hope you were able to learn something, and I hope to see you later. Consider leaving a like and subscribing, and thank you for watching.